Okay, we ended by finding the Maclaurin series for e to the x. The fact that e to the x is equal to this series means that the limit of the series is e to the x. But the thing is, ideally, we can only compute a finite number of terms, so we want to understand um, what the error term is going to be. So if we let Tn be the partial sum, so instead of going to infinity, we are going till n. For this function, for example, t1 would be 1 plus x, t2 is 1 plus x squared over 2, t3 is this, and so on. What we are essentially saying in the previous video is that f of x equals limit of the partial sum. And if we let Rn be this difference between the function and the Taylor polynomial, then Rnx is called the remainder of the Taylor series. This is called the Taylor polynomial. We use the word polynomial because n is finite. So you stop at a certain power of x, that makes it a polynomial. A power series is not a polynomial. If your function is the sum of the Taylor polynomial and the remainder, and the limit of the remainder is 0, then f equals to the sum of its Taylor series on this interval. This is just a fancy way of saying that if your remainder under the limit is 0, then under the limit, the Taylor polynomial equals the function. Now, in order to study that, there is an inequality which says that if the n plus 1th derivative of f at x is less than m for some values of x, then the remainder satisfies this inequality, that it's always less than m times x minus a to the n plus 1 over n plus 1 factorial. Why this is important is because this gives us a bound on the remainder, which means by taking the limit, we can find out what the limit of Rn is. Prove that e to the x is equal to the sum of its Maclaurin series. So basically we want to show that this particular formula is good. In order to do that, what we notice is that first of all we need to find fn plus 1 of x is e to the x, right? So for a fixed, if I let x is less than d, then the n plus 1th derivative at x is going to be less than e to the d. Then this result right here says that the remainder Rnx is going to be less than e to the d x to the n plus 1 over n plus 1 factorial. So the limit as n goes to infinity of the remainder is going to be e to the d limit n goes to infinity x to the n plus 1 over n plus 1 factorial, which is 0. Right? So if this goes to 0, this means the proof is complete, and it means that e to the x equals its sum of its Maclaurin series. Find the Taylor series for f of x. E to the x at a equals 2. So what we have is f prime of x is e to the x. Now f prime of 2 is e squared always. So the series is going to be n equals 0 to infinity. It's always fn at a over n factorial x minus a to the power n, which becomes e squared over n factorial x minus 2 to the power n, summing from 0 to infinity. Some more examples of Maclaurin series. Finding the Maclaurin series for sine x. First of all, this means I'm working with fx sine x. F prime x is cosine. The second derivative is negative sine. The third derivative is negative cosine. And the fourth derivative is sine. So after 4, the pattern repeats. So Maclaurin series, so which means I can find f of 0, which is sine of 0, which is 0. F of 1, or sorry, f prime of 0 is cosine of 0, which is 1. F double prime of 0 is negative sine, still 0. The third derivative is negative 1. The fourth derivative is 0. So again, this pattern is going to repeat. Which means what I have is that I have f of 0, f prime 0, 1 factorial, f double prime 0, 2 factorial, x, x squared, f triple prime 0, 3 factorial, x cubed, f fourth derivative, x to the 4, 4 factorial, so on. So I have sine x equals, that's 0. So I start with 1. 1x over 1 factorial, that's 0. Negative x cubed over 3 factorial. And because of the pattern, x to the 5 is going to be positive, and then x to the 7 is going to be negative, and then x to the 9 is going to be positive, and x to the 11 is going to be negative, and so on. Now, why is this a good representation? Because if you look at the nth derivative, it's always going to be less than or equal to 1. It's either sine or cosine, which means Rn of x is always going to be less than 1 times x to the n plus 1 over n plus 1 factorial, which under limit goes to 0, which means that this is a good approximation. Now let's find the Maclaurin series for cosine x. Multiple ways of doing this. You can go through the same process as you did for sine, or you can be a little smart about it and remember this is a power series, which means you can take the derivative. Derivative of sine x is cosine x, and this becomes 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus 6 factorial, and so on. Let's verify that the factorial thing works out nicely. Okay, some more examples will be covered in the next video.